to see there with that one. So starting at 17, 29, 31, and 45, you can't see those over there. Those are the problems that I wrote in the thing. Anyway, on this first one, they say specify which of the following equations represents oxidation reduction reactions, indicate the oxidizing agent, the reducing agent, the species being oxidized, the species being reduced. So first thing I'm going to do when I look at these is say, is something changing charges, right? So I'm going to look for somebody changing charges. Since there's an element here and no other elements, that right away, yeah, there's somebody changing charges because it has a charge here and it doesn't over here. So since oxygen's -2, hydrogen must be +1, and over here it's 0. So absolutely, yes, this is a redox equation. Since I've already found the hydrogen's going from +1 to 0. How does it do that? It gains in electrons. Gaining electrons is a reduction. So this is the thing being reduced. So that means that H2O is the oxidizing agent. Oxidizing agent. There we go. I'll just write fast so you can't read that I can't spell the word oxidizing. All right, so that's my oxidizing agent. It is a thing being reduced. When I look at the other things, my guess is that the carbon is probably the other thing getting messed with here. In this case, when hydrogen is with anybody except for metals, it's a +1. So this is a +1 on this. So my hydrogen's a +1. My carbon is therefore then a -4. Carbon here is a plus. That's a -2. So the carbon is a +2. So the carbon goes from a -4 to a +2. So it does that by losing electrons. So the carbon is losing electrons. As it loses electrons, it is oxidized. It is the reducing agent, all that kind of stuff, right? If we look at another one there, the second one, if you couldn't do the first one on your own, try and do the second one on your own, the silver nitrate one. So the second equation, again, is it a redox equation? Well, I see an element and not element, right? Compound. So yes, redox equation. That's not the only thing. You can have redox equations that don't have just a pure element in them, but that is an easy way to recognize it pretty quickly. My silver is +1 to 0. That means that is gaining an electron. That means it is being reduced. That means my silver in my silver nitrate is my oxidizing agent because the silver is getting reduced, so the silver is the oxidizing agent. Copper is going from 0 to +2, so that means my copper is losing electrons. Leo says Gur, losing electrons is oxidation. So if my copper is being oxidized, it is the reducing agent, right? When we look at the other ones, C is also a redox equation. Is D also a redox equation? D, hang on, let me play with that first. I was going to just run through those last ones real quick and say if they're redox or not, because we'd already done a couple, but this one's not quite as obvious, right? So I glance at this one, I see a transition metal. It's not immediately obvious that transition metal has changed charges. I see hydrogen here, but I don't see that hydrogen has changed charges here. So my initial thought is maybe this is not a redox equation, but I'm going to check this chromium to be sure. So we've got -14 here, and there's 2 of these, so that's +6. +6, that's +12, -14 is -2. Remember, the total charge needs to add up to the charge there. We then have a -8, so this guy must be a +6. So it did keep the same charge, even though it looks different. The chromium kept the same charge. Oxygen is -2, so that's a +1 and a +1. So this guy here is a +1. So nobody's changing charge there. So that is one that is not a redox equation, but wasn't immediately obvious because the chromiums kind of looked a little different there. In just like a double displacement or an acid base, you can sometimes tell right away that it's not a redox equation. Right, so that is 17. 29 is balancing redox equations, so using the half reaction method. So I'm going to go I minus goes to I3 minus, then I'm going to do ClO minus goes to Cl minus. Step 1 is to balance everything that's not hydrogen and oxygen. So we do that. Those are good as they sit. So then I need to put an H2O over here and 2 H pluses over here. Then we figure out what we're talking about electron-wise. Overall, this is -3 total overall here we are -1. So this must be +2 electrons here, right? That one's kind of weird looking with the I3 minus there, but overall there's a -1 charge on that whole thing, whereas here you have 3 things with a -1 charge. Then we look at our chlorines. We have oxygen here that has a -2 charge. Chlorine must then have a +1. Here, chlorine has a -1, so that's going to be +2 electrons. So this one's going to be pretty easy because your electrons are already balanced out. So all I would need to do is come back up here and put a 3, put a good, and then we just add in our other stuff there. No, it's not 2 H2Os, it's just H2O. And over here we got our 2 H pluses. And looks like we're good to go, right? So that would balance that one out for a redox equation. The next one on 29B, you've got this arsenic oxide compound, and then nitrate ion, and then we've got an acid. This would be ASO4. That's probably, is that per? That'd be a per ion, or just an arsenate? Probably just an arsenate. Yeah. So it'd be arsenic acid, I guess, right? And nitrogen monoxide. So we break that up into our 2 half reactions. The first thing I need to balance, I've got 1 arsenic here and 2 arsenics here. So we'll put a 2 here. Then we need to fix our oxygens. I have 8 oxygens here and 6 here. So 2 waters there, right? So I have, oh no, I only have 3 here. 3 oxygens and 8 oxygens, right? Yeah, 3 and 8. So that I need 5, right? So 5 plus 3 more is 8. 2 times 4 is 2 there. Then I've got 6 hydrogens here, and I've got 10 hydrogens here. So I would need another 2 H pluses over here, right? Getting kind of weird with the oxygens on that one, but just double check and count things and that kind of stuff. So I've got 6 hydrogens, 2 bonus ones, 6, 7, 8. Oh, I need 4 bonus ones. I really am. I'm struggling on this one. It's a rough day. So 6 and 4 is 10, and 5 and 2 is 10. 2 arsenics, 3 oxygens, and 5 oxygens is 8. 2 times 4. Okay. Yeah, I don't know. That was tough. Anyway, then we have our nitrate to our nitrogen monoxide. So we'll do 2 H2Os over here to balance out my oxygens. Then I have 4 H pluses, so 4 H pluses over here to balance that out. Then we need to figure our charges. So going to be the arsenic that's having issues here, so that's -6. So this must be +6. Remember, totals is what I care about. Each one of them is +3. The total is +6. So this is -8. This is +3. So then the leftovers here must be +5. And there's 2 of those, so that's +10. Right? So we go from +6 to +10. So it's a 4 electron difference. So +4 electrons on this one. Then we have our nitrogens that -2, so this must be a +2. -6, so this must be a +5. +5 to +2, we must have 3 electrons over here. This one is just ugly all around. This is all kinds of ugly. So to balance these out, you've got a 3-4 situation. So 12, looks like we're going to multiply both sides by 3 and 4. So we multiply this one by 3, so that becomes 15. That becomes 3. This becomes 6. This becomes 12, and this becomes 12. Multiply this bottom one by 4. This becomes 12. This becomes 16. This becomes 4, 4, and 8. Now I recombine everything. This is, do the easy ones first here to just get them out of the way. Now waters, I have 15 over here and I have 8 over here. So that means I have 7 left over here. 7 H2Os here. H pluses, I have 12 over here and 16 over here. So I have 4 extra over here plus 4 H pluses. So if we count everything out, which I'm not going to, can you see all of that? You can't see all of that. I'll pause it and count to double check that everything's good, but we should go back now and count all of our spectators and all that kind of stuff, right? So the waters and the H pluses aren't usually on the same side, but they can be. And when you look at how many oxygens and stuff we have here, it kind of makes some sense.